Не знаю, так слышно? Can one hear me? Online. Well. So let's start. Today we will classify all the subgroups of G, that is GL and FQ. It turns out that in a sense classification is independent of Q or over the ground field at all. Well, it's only depends on characteristics, so to say. So we start with a lemma that the order of an element of our group is divisible by P, that is the characteristic of our ground field, if G is a conjugate to an element like this. Okay, and the proof is immediate. Well, just the Jordan normal form over the algebraic closure of our field. Okay, and the corollary is that if we have any subgroup, not necessarily normal, and if we know that its order is divisible by P, then either K is contained in some Borel subgroup, or maybe it's conjugate, or K contains some conjugate of some SL2. Like this, for some subfield. Okay. And the proof is easy again. So are you going to stay or just want to give me the card? Then maybe you can give it to Sinja. Thank you. And then when you come to Skoltech, please give it to the guards. When you just enter this building, they asked to return this card, so please return it next week. Thank you. Okay, so how do we prove this? Well, we choose an element, say K, in this group of order divisible by P. Since the order of the group is divisible, there must be such an element of the order divisible by P. Then we know that it looks like this. But now this A has it's a well, A scalar matrix is central, and it has order prime to P. Yeah, it's invertible in our ground field. So if we take its appropriate power, we will get just the unipotent matrix here. yeah, then by lemma, k to some power, whatever, m, is in the upper triangular subgroup. Okay, and so well, there is an eigenvector with eigenvalue 1. Well, let's say k1 equal to k to the power m, and k1 v1 is v1 for a basis element. v1 in two-dimensional space. Okay, and either all k preserves this line, all our group kv1 is lambda v1, or there is k2 such that k2 well, say v1 and v2 equals k2 v1 is a basis of our two-dimensional vector space, but then k1 and k2 generate a subgroup SL2 f prime, sorry, f for some subfield f, as we argued last time. Yeah, we argued that say for the prime field SL2 is generated by two elements. So for the second element I took this particular 0, 1, negative 1, 0, but doesn't matter. Any element which is not in Borel will generate the whole SL2 along with this upper triangular subgroup. So we're done. So this was about the groups of order divisible by p, and now we turn to the groups of order not divisible by p, and this classification is independent of the field. So for example, it's the same over complex numbers. Any field would work. So consider a subgroup of order not divisible by p, and its quotient, its image in the quotient modular scalars. And then this quotient is of the following possible forms. Either this is a cyclic subgroup, and then K lies in a Cartan subgroup. And there are two types of Cartan subgroups, namely split, that is diagonal matrices, and non-split, namely you take quadratic extension and its multiplicative group in GL2. Yeah, we discussed something like this last time. Now, another possibility is that K over line is dihedral, and then K lies in the normalizer in G of this Cartan. that is, well, for diagonal matrices, this is something which is generated by the Cartan itself, and this W element. Okay, and the only remaining possibility is that K, the image in PGL2 is of type A4 or A5 or S4. Yeah, so well, this corresponds to tetrahedron. This corresponds to icosahedron. And this corresponds to octahedron or a cube. Okay. And now the proof is probably very well known, but yes. Well, again, maybe well, I should say it could be conjugate to this. So what's the question? Carnot subgroup is by definition what well, I don't. Maybe I shouldn't go to the abstract general definition, but just say that it's either there are two types of Cartan subgroups. First type, they are conjugate to diagonal matrices. The second type, conjugate to this. But well, abstractly, say over the over the algebraic closure of our field, they will all be conjugate to diagonal matrices. So there are various forms of diagonal matrices over non-algebraically closed fields. Okay, so the proof is very well known. I don't know, maybe everybody knows, and I should skip it, or shall I remind it? Okay. So you may imagine that the ground field is complex numbers, okay? And I mean that in this case, probably I've seen this argument before. So we consider the projective space of over our ground field. So if the ground field were complex numbers, then this P1 is just the Riemann sphere S2. And now we consider the pairs, an element, non-trivial element, say G, not equal to identity in G, and a point, say a line in P1 such that it is fixed by our element. In other words, it is spanned by an eigenvector of G. Okay. Now, maybe say Li's are representatives of G orbits of such eigen lines. Okay, and maybe yes. Yes. No, I don't claim that any element has eigenvector. I just consider the possible pairs, yeah, an eigenline and the corresponding element. So I don't claim that any element will enter in this list. Mm, okay. Uh, so Ki is the stabilizer of Li. Hi is the order of this stabilizer. And H is the order of projectivized group of ours, the K over line, the Imogen PGL2, because PGL2 embeds into automorphisms of projective line. GL2 does not embed the central elements act trivially, but PGL2 embeds. Okay. So the number of pairs G and L is 2H minus 2. Why? And maybe to make it true, let's consider, as you suggested, the algebraic closure, so that indeed any element does have an eigenline. So now. So first of all, it's not eigenvalue, it's eigenvalue. It's a German word, so it's called eigenvalue. And second, now each element does have an eigenline, but it could have just one eigenline. Yeah, if it were a unipotent element, it would have just one eigenline. If any element has exactly two eigenlines, since we do not allow the unit element, we will have 2H minus 2. But we must make sure that there are no unipotent elements. Why there are no unipotent elements? Yes? G is from K bar, yeah. Sorry, maybe I should say, yeah, sorry. Thank you. So why there are no unipotent elements? Just by our assumption. Maybe you cannot quite see it, but the assumption was that K is not divisible by P. And our first lemma says that there are no unipotent, or up to center. No elements like A1. Okay. On the other hand, it is equal to the sum over all I, all the orbital representatives of 1 over Hi times Hi minus 1. Maybe just count over orbits. Okay, so we have such inequality. And now, if you just divide by h, it means that 2 times 1 minus 1 over h is equal to the sum of 1 minus 1 over hi over I. Pardon me? Sorry, here it's h. Yeah, yeah, sorry. Okay, so then we have such an equality, and it has, well, not many integer solutions. Namely, let R be the number of orbits so we sum here from 1 to R. Okay. Then the solutions are as follows. We can have R equals 2, and then H1 equals H2 equals H equals 2, or else R equals 3, and then H1 equals H2 equals 2, and H equals 2 H3, or else R equals 3 and H equals 12, and H1 equals 2, H2 equals 3, H3 also equals 3. So this is cyclic, dihedral, tetrahedral, now octahedral. Again, R equals 3, and H equals 24, H1 equals 2, H2 equals 3, H3 equals 4, and finally R equals 3, H equals 60, H1 equals 2, H2 equals 3, H3 equals 5. Okay. Well, it depends. There are many dihedral groups. Depends on the order. Okay, so that's it. And maybe let me just state the last proposition of this form about classification of subgroups of PSL2 FQ. The simple group, we proved this last time. So either subgroups of Borel, or maybe we'll call it B prime, yeah. So they're either cyclic or solvable. Then also subgroups of the normalizer of Cartan. So they are dihedral. And then finally we have this A4, S4, and A5, and also we can have well, also we can have PSL2 for a smaller field, and finally we can have something which is generated by this PSL2 over a smaller field, and one other element, pi diagonal element, such that pi does not lie in F, but pi squared does. Okay, so this is the end of classification. And now let's go to some most important technical tool I promised last time. So these are induced representations. Okay, and so we have a subgroup H in a group G, and now G is some abstract group, not necessarily GL2. And we have a representation tau W. So it's a homomorphism from H to automorphisms of W. Okay, and then one can define the induced representation from H to G of W, or sometimes it's denoted like this, or whatever. So it is by definition certain space V of functions f from G to this space of H module that are sort of equivariant with respect to the action of H. That is, f of H G is equal to tau of H f of G. Okay, and now this is a representation of G, namely G acts here very naturally. G f is well, yeah, G f of maybe G prime, like this, is f of G prime G. Okay. Now, have anybody seen this before? Great. Yeah, great. Just two of you? Three of you. Great. Okay. So now, well, given a basis in this representation W, I can produce some other basis in this induced space V. Namely, first of all, we have an embedding from W into the induced representation, but only as an H module, not as a G module. Namely, W goes to the corresponding function Fw. So this Fw of G is either tau of G W if G lies in H, or 0 otherwise. Okay, and now G decomposes into the cosets. But I have a psychological problem, or maybe mental problem. I always forget how do you say it's left cosets or right cosets? Probably right cosets, yeah? Yeah? Yeah, I also have such problems. So you say that's called left cosets? Are you sure? Left? Okay. Sorry, yeah. In fact, for many years since my childhood, I could not distinguish between the capitals of Poland and Czech Republic, between Warsaw and Prague. I always confused them. Now I learned to distinguish them, but not with right and left cosets, unfortunately. Pardon me? Right, yes. But to make things worse, Warsaw has a district called Prague. Well, like for example, Boston in Massachusetts has a district called Cambridge, and both Harvard and MIT are exactly in this city called Cambridge, inside Boston. Okay, so yeah, we have this decomposition into left cosets, and for a function f in V in this induced space, we can decompose it into corresponding summands corresponding to cosets. Or zero otherwise. Okay, and then certainly f is the sum of such things. R applied to R inverse fr, and hence the whole space V decomposes into the sum of copies of W over the right cosets, sorry, left cosets, sorry. Okay, and then what it implies is some rather algebraic definition of induction well, I mean that this definition is it's applicable in very wide variety of situations. For example, to complex or real groups, not necessarily finite groups, and it is formulated in terms of functions, so it's sort of analytic one. But there is an algebraic definition, namely that it's just well, G modules are the same as modules over the group algebra of G. Do you know this? Yeah. So then, in terms of group algebras, you just take the group algebra of G, and it is acted upon by the group algebra of H, both on the left and on the right. And so we can tensor over the group algebra of H with this W to obtain V. Okay. So this is this decomposition over the left cosets. Right, absolutely, yes. Absolutely, just this. From H to G. Or strictly speaking, from the group algebra of H to the group algebra of G. Absolutely. Yes. Fine. And then two basic properties. They're more or less clear from this definition. Namely, first of all, transitivity. That if you have a flag of subgroups like this, then the induction from the smallest to the biggest is the recursive induction. So if you first induce from the smallest to the intermediate one, sorry, and then reduce from the intermediate one to G. Okay, and the second property is the famous Frobenius reciprocity. I mean, apart from extension of scalars, certainly there is a restriction of scalars. Certainly I can restrict representations from the big group to a subgroup. And then these two operations are related. So in scientific language, the functors of restriction and induction are adjoint. And since we are working with finite groups and representations over complex numbers, then all representations are semi-simple, and there is no somehow difference between left and right adjointness. So they are both left and right adjoint of each other. And do you know these words? Left and right adjoint? Okay, then. We are in business. Maybe there are better. No. But maybe you know from basic representation theory that in order to find the dimensional space of homomorphisms from one representation to another, you just take scalar product of their characters. Do you know this? And it's in this formulation that Frobenius found his reciprocity law, because he first dealt with characters, not with he didn't know that there were traces of something else, of representations. So anyway, so homomorphisms over G from induced representation to something else is the same as homomorphisms over H from this representation W to the restricted from G to H representation E. Okay, and you can, well, so say in this interpretation, you can immediately construct a map in one direction and see that it's an isomorphism. Okay, and now we will just repeat. I mean, I will state the fifth home assignment problem. Okay, maybe you have seen it already. So problem 5. Suppose I have two different subgroups, and now they do not form a flag, not necessarily form a flag, just arbitrary subgroups. So they have representations V and rho and W and sigma, and then you induce, and you wanna find homomorphisms over G from representation induced from H into representation induced from J, like this. And this can be sort of, well, in a sense, explicitly calculated. And this is a theorem going back to George Mackey. And certainly he stated and proved this theorem not in this baby case of finite groups, but in some for some L2 representations of real groups, or at least for compact groups maybe. Okay, so the answer is as follows. So this is isomorphic to a certain space F, and F consists of functions from G to just linear maps from V to W, but such that F of J, G, H is equal to sigma of J, F of G, rho of H. Okay, and this Mackey isomorphism is constructed as follows. So you send F to certain intertwining operator T sub F, and this T sub F acting on a function F evaluated at G is 1 over the index of H, the sum over all elements, F of GR inverse, F of R. So your problem number 5 is to check that this is that this makes sense and that does give you an isomorphism. And the corollary, maybe even 2 corollaries, very useful, are that the dimension of this home space between 2 induced representations is not more than the number of double cosets times dimension of V times dimension of W. Okay, and the next corollary is about the case when these 2 groups coincide. If they coincide, then we're speaking of homomorphisms from the induced representation to itself, that is to endomorphisms of this induced representation. But the endomorphisms, they certainly can be composed, so they form not just a vector space, but an algebra under this composition operation. And it's interesting to describe this algebra structure, multiplication, composition, in terms of this Mackey realization script F. Okay, and the answer is as follows. So how to multiply elements of F in case the 2 subgroups and representations coincide. If J equals H and V rho equals W sigma, this home is and forms an algebra, and the multiplication on F is given by sort of convolution. F1 convolution F2 of G is again 1 over the index of H and G, the sum over all elements in G, F1 of G S inverse, F2 of S. In fact, the multiplication in the group algebra of G is given exactly by this formula, by this convolution, and you just restrict it to, well, I don't know, maybe not restrict, but just write the same formula. Okay. We will use this abstract things later on, and now we return to the particular study of our group GL2 FQ, and first we study the representations of this mirabolic subgroup P, like this, and B, Borel subgroup. Okay. Well, in fact, B is just the product of this mirabolic subgroup times the center. The center is just the multiplicative group of our field. So if we know the representations of P, then we know representations of B. So we start with P. Okay, and then P clearly is the semi-direct product of A and U. So U is upper triangular. Sorry, 1 like this, and A is diagonal. Yes. Yes. Well, we identified this space of intertwining operators, the homomorphisms, with certain space of functions, right? And now, in terms of this identification, the composition of endomorphisms gives you an algebra structure on F, on a space of functions. There is certain multiplication on F, just corresponding to composition of endomorphisms. And then I claim that this operation of composition is given by this convolution.
Is there some one element in this structure?
What is one? Yeah. Yes, certainly, and maybe you can guess what is the unit element.
Well, the image of identity, but
Absolutely, yes. So what will it be? Just absolutely explicitly, and which function f corresponds to 1? You see, it cannot be just a delta function of the unit in the group, because it must be a sort of equivariant with respect to h. So its support cannot be that small. What is its support? What is the smallest possible support? Huh? No. Pardon me? Which element? I cannot hear you. But so now we're discussing the question: what is the so f is the space of functions from G. So if I am after the identity homomorphism, it corresponds to some function. What is the support of this function? It's some subset of G. Right. So Absolutely, yes. So, right, it's H. Okay. And now it's some function from H into homomorphisms. And what is the value of this function?
So then it will be just endomorphism, yeah, of
Right, yes. Just endomorphisms of our representation, say V.
well, it's probably just the representation itself. Yeah. Is it just one?
No, so to some function f, and as you say, the support of f is h, so it's a function f from h to endomorphisms of v, and what is h goes to what? Yes, absolutely. Yes. Okay, just this. Then it satisfies our basic relation, and this will be just the unit element.
If you see this basic relation, should it be like rho squared or something?
No, I don't think so. No. For example, f of 1 is 1, but then you. Okay. So we have now A is just the multiplicative group of f of our basic field. This is the additive group of our base field, and then in the second set of home problems, you have something about this, and it's not an abelian group. So certainly it projects. Well, there is an exact sequence. 1 goes to U, goes to P, goes to A, goes to 1. But then there is a section. It's a semi-direct product. Okay. So every character of A, certainly just with composition, by composition with this projection, gives rise to a character of P. Character, I mean, one-dimensional representation, homomorphism to the multiplicative group of complex numbers. But it turns out that there is just one more irreducible representation of P. So the answer will be Q minus 1, one-dimensional, well, just characters. Characters of P, well, factoring through the projection P to A and then to C star, and one more irreducible representation of dimension equal to Q minus 1. This will be the answer. And the question is how to construct this irreducible Q minus 1 dimensional representation of P. In fact, in your home assignment, there is some construction, and then there are some problems about Fourier transform, and it's not just for fun, because in a sense the construction in the home assignment is Fourier dual to what we will have now. So if you still don't know about Fourier transform, but by the way, do you really know about Fourier transform? Say over finite abelian groups. or over reals? So over reals you do know, but over finite groups? Mhm. Ah, pardon me, in analysis? What? Uh, oh, but what about Fourier transform? I don't hear. You do know? Too much. But something you do. No, the general idea, especially for finite groups, it works over pretty large class of groups, say over real numbers or p-adic numbers or whatever, any locally compact abelian groups. The idea is that the characters, just one-dimensional representations of locally compact abelian groups, they form a pretty wide class of functions, complex valued functions. In a sense, they form a basis in appropriate functional spaces. So given an arbitrary function, you can decompose it with respect to this basis. And the coefficients of this decomposition, well, they may be viewed as another function from the set of characters to numbers, to complex numbers, just coefficients of this decomposition. And this function from the set of characters to complex numbers is called the Fourier transform of the original function. Because the characters also form a group, right? You can multiply characters. It's called the dual, Pantryagin dual group. So there is this transformation from functions on original abelian group to the functions on its Pantryagin dual. And it's called Fourier transform. In the case of, well, in case of real numbers, it's not quite sum, it's rather integral, and there are some analytic difficulties. But in case of finite groups, there are no difficulties whatsoever. And there is some elementary definition which I give in the home assignment. Okay, but so far we don't need anything of this, but we need some construction of this representation. Can anybody suggest any construction of this representation? Well, certainly we didn't study induced representations just for fun. Yeah, certainly I expect this representation to be induced, but from what subgroup and what representation? For example, if say you take a trivial representation of any subgroup, just trivial representation, then what will you get by the very definition? No, by no means. For one thing, is the dimension depends on H. The dimension will be the index Yeah, unfortunately, I just erased the definition of induced presentation, but maybe you have some notes. I mean, there is some general definition, but it somehow simplifies in this case when you apply it. Pardon me? Pardon me? Maybe, but just I wonder if you reduce trivial representation in general, what do you get? Well, what I mean is, yeah. Well, sort of, yeah. So it's just functions on cosets, yeah, like this, and gx just by right translations. So if you have like this, right? So just a sort of homogeneous space, and gx there naturally, and then it acts naturally on the function of the space. Okay, so as Shuai says, we could certainly, judging by the numerology, we could consider induced representation from U to P of say trivial representation, but that's not interesting because I mean it's interesting, but certainly not irreducible because this U happens to be a normal subgroup. So the left cosets the same as right cosets, and it will be utterly decomposable. This will be just the regular representation well, functions on A. Just AX on itself, PP projects onto A, and the action of A on itself well, decomposes the regular representation into just all the characters. So this will not be not irreducible. Dimension is okay, yeah. Dimension is q minus 1, but unfortunately it's not irreducible. And if you want to obtain an irreducible representation, what should you do? Yes. Yeah, it's a good idea, but the dimension is wrong. So what shall we do? Right, right. So Signor says the correct answer. We should induce from U to P, but not trivial representation, but non-trivial, some non-trivial character. So this will be the solution. And now what about characters? So indeed there is one preferred character. How do, well, it's also constructed in the home assignment. So from U, which is just FQ. Well, U equals FQ, and then you go to C star. So it's called an additive character. Well, we'll discuss this in a moment. I will first somehow classify all the characters in a sense. Yeah, in fact, any non-trivial character will do. They're all the same. So there is one preferred character, and how to do this? Well, FQ is an extension of FP, and so you have the trace homomorphism like this, trace from this field extension from Galois theory, yeah, you know, and then here you have sort of exponential character, namely FP is just Z modulo PZ, and then well, here you have a number K, and then K goes into the exponential of 2 pi I K over P, like this, yeah. So this composition is called psi, one preferred character. But then from another point of view, they are all the same. Namely, there is a multiplication action of F Q star on FQ. Yeah, just you can multiply by any number, and it's in fact it's the same as from this point of view as the conjugation action. Yeah, so if you take A 0 0 1 1, say U 0 1, A inverse 0 0 1, then what do you get? What do you get? Well, maybe you need to compute something, not just contemplate it philosophically. That's true. How do you know? Just in your mind without? I envy you. Okay. Um, okay, so just multiplication. Action is this conjugation action. And then psi A of u, by definition, is this particular psi of A times u. Okay. And well, this is the key to irreducibility, because when you induce, if you remember, inside this space of induced representation, it contained the original representation as an H submodule. Submodel with respect to the subgroup. Yeah, but then you can act on this subspace by the elements of the ambient group G, and you will obtain some other subspaces, but as H. If H is a normal subgroup, then from the point of view of H, these other subspaces will be just the conjugate representations. So I mean the ambient group acts on subgroup by conjugations, and the other representations of H you obtain in this decomposition are just conjugates of the original one. And now you see that the conjugates will be just these dilations of your character, and all the possible characters are obtained in this way. So in your home assignment, you are supposed to prove that any character of FQ is psi A for some A. And in fact, well, this one-to-one, this is exact classification. For two different A and B, these characters do not coincide. Okay. So, well, lemma is that if you restrict from P to U the induced representation from U to P from non-trivial character, then you just get the direct sum of psi A for any A in FQ. But the dimension is Q minus 1, so this A must be non-zero. So the trivial character does not enter, all the non-trivial characters. Okay, and just the proof is very easy. So for any A, we define the corresponding function fa in the induced representation of psi, fa over whatever b is equal to 1 in case b mod u is A and 0 otherwise. Okay, and then this is an eigenvector well, we have this exact sequence. Right, so given an element here, well, we have its image in the multiplicative group. Okay, there's an eigenvector of U with eigenvalue psi A. Okay, and well, that's it. And then the classification theorem I announced is that P has Q minus 1 characters factoring through the projection to A, and one irreducible say pi of dimension Q minus 1. And the proof of irreducibility is again immediate. So just by Frobenius reciprocity, the endomorphisms of pi are the same as homomorphisms from psi to the restriction of pi from P to U. But we know that this restriction decomposes into the sum of all characters with multiplicity 1, so it is just C. But the endomorphisms of a representation equal to C if and only if it's an irreducible representation, right? Just by Frobenius reciprocity, because it's well, this okay. Just because we computed in the lemma this restriction, and it is the sum of all non-trivial characters, in particular psi enters just once. And all the other characters are different, and so there are no homomorphisms. Maybe I should write okay. Now, strictly speaking, we have to check that there are no other representations. So certainly we could count the conjugacy classes, for example, or else we could count the sum of squares of dimensions of representations, right? So for finite groups, there are many ways to check that your would-be list of all irreducibles is really complete. But the point, as I mentioned in the very first class, is that this representation theory is miraculously persistent. So it works over any fields, in fact. Say over complex field, real, p-adic, whatever. So if possible, I would prefer the arguments that at least have potential to work over arbitrary field, where we cannot count the number of representations, for example, since there are infinitely many representations. So I prefer some other argument, and this other argument says that if say rho is another irreducible representation of P, then if the restriction from P to U of rho contains any non-trivial character psi A, then the home space from pi to rho is again one-dimensional by the same reasoning, and so since both are irreducible, pi must be the same as rho. Okay. Otherwise, the restriction from P to U of rho is trivial as a U module, and then it is the restriction is the direct sum of eigenvectors. Well, maybe even not the representation itself. Rho itself is direct sum of eigenvectors of A. So restriction to U is trivial, hence rho factors through the projection onto A, and then we just know that all such are characters of A. Okay. So we are done, and the time is up. Thank you. And next time we will deduce some classification of Borel representations. It's trivial because it's just the direct product with the center. But then we'll start inducing from Borel to the whole of GL2, and this will be interesting. In fact, this is what is called the principal series representations. I mean, for generic representation of Borel, its induction to, or maybe generic character of Borel, its induction to GL2 will be irreducible, and it's called principal series representation. Okay, but then next week I will be away, so we'll meet next time on January 31st, next Tuesday. Not next, but in a week. Thank you. Now I have to press 2 buttons, but I don't know how to even. There's a black screen. How do I? I'm afraid if I touch it, I can press something wrong. Don't know how to do it. No? Oh. Thing wrong. Don't know how to do it. No?